124 light-years from Earth, in the constellation Leo, there is a planet 2.5 times the size of our own. The James Webb Space Telescope has now pointed at it 3 separate times, and what it saw, the 3rd time, made scientists go quiet. A faint chemical fingerprint flickered in the planet's air, and on Earth, only one thing produces that fingerprint in any real quantity: living organisms. Tonight, we walk to that planet together. We meet the cool red sun it orbits, the team in Cambridge that proposed it might be alive, and the 3 other research groups who quietly took the same data apart and arrived at a different answer. If this kind of careful, patient science fascinates you as much as it does us, hit subscribe so you never miss what Webb sees next. Get comfortable, we begin. The constellation Leo is one of the older shapes in the sky. It sits along the path the sun takes across the year, and most of its stars are bright enough to find from a backyard on a clear night. But the star we are about to talk about is not one of those. It is too faint to see with the naked eye. You would need a telescope to find it, and even then it would look like nothing in particular. A small red point of light, almost lost among brighter neighbours. That small red point has a catalogue name, K2-18, and around it, in a tight orbit, is a single planet that almost nobody outside of astronomy had heard of a few years ago. The planet is called K2-18b. It is the second object discovered in this system, which is why it carries that lowercase letter. It is smaller than Neptune and larger than Earth, and it is the reason an entire branch of exoplanet science has been quietly arguing with itself for the better part of 3 years. The James Webb Space Telescope has now watched this planet 3 separate times. That sentence sounds simple. It is not. Webb does not watch planets the way a camera watches a face. It watches them through their own star's light, in the tiny window when the planet passes between us and that star, and the light filters through the planet's atmosphere on its way to us. Each of those windows lasts only a few hours, and the planet's year is 33 days, so if you miss a transit, you wait another month for the next chance. 3 transits, 3 different instruments, all under one program. The program has a number. It is 2722. If you open that program file at the Space Telescope Science Institute in Baltimore, you would see, listed inside it, 3 near back-to-back appointments with the most powerful infrared telescope humanity has ever launched. All of them dedicated to one planet, 124 light-years away, around a star that is, by every ordinary measure, completely unremarkable. That is the title of tonight's story, in literal form. Webb cannot stop watching this planet. The question is why, and the answer, when you look at it carefully, is not what most headlines have said. The headlines, almost from the beginning, have wanted to talk about life. Life beyond Earth, life on a distant ocean world, the first hint of biology outside our solar system. Some of that conversation is fair, some of it has been overstated, and almost all of it has skipped over the slower, more interesting story underneath. Before we keep walking, it is worth pausing on what Webb actually is, because the telescope itself is part of why this story is happening at all. The James Webb Space Telescope is not in orbit around the Earth, the way Hubble is. It sits about 1.5 million kilometers beyond the Earth, at a point in space called L2. L2 is one of 5 special locations where the gravity of the Earth and the gravity of the Sun work together in such a way that a spacecraft can hold a steady position relative to both. It is, in effect, a parking spot in the gravitational landscape of the inner solar system. Webb hovers there, perpetually on the night side of the Earth from the Sun's point of view, shielded from solar heat by a large silver sunshield the size of a tennis court. Behind that sunshield, Webb's main mirror is 6.5 meters across. It is made of 18 hexagonal segments, each coated in a thin layer of gold, fitted together so precisely that the entire surface acts as one continuous mirror. Gold is used because it is highly reflective at infrared wavelengths, and infrared is the kind of light Webb was built to see. Because Webb is parked so far from any source of heat, and because it is so well shielded, its instruments operate at temperatures close to absolute zero. That cold is essential. Infrared light is, in essence, heat. A warm telescope would drown its own measurements in its own glow. Webb is kept cold so that the faint infrared signals from distant worlds can be heard above the noise. That is the instrument that has been pointed at K218b 3 times, a 6.5 meter cold gold mirror, in a position nobody can casually visit, collecting photons that left a planet's atmosphere 124 years ago. The fact that this is a routine event in modern astronomy is itself one of the strangenesses of our current era. We're going to walk through that slower story tonight, not as a debunking, not as a celebration, as a careful look at one planet, one telescope, and what we actually know, against what we have only suspected, against what we are still arguing about. The science is real. The arguing is also real. Both are part of how we get from a smudge of light to a sentence about what kind of place a world might be. So before we go any further, if this kind of careful, patient science is the sort of thing that helps you wind down at the end of a long day, then hitting subscribe genuinely helps this calm corner of science reach more people who might need a quiet evening among the stars. That is the only thing we will ask of you tonight. The rest is just a walk. The planet itself was not discovered by Webb. That is the first thing to clear up. Webb is too new to be a discoverer of small planets like this. It came online in late 2021 and began full science operations in 2022. K2-18b was already a known world by then, with a name, a measured mass, and a measured radius. It had a paper trail going back to 2015. It even had an early hint from a different telescope that there might be water in its atmosphere. Webb's job, when it finally turned to this planet, was not to find it. It was to look at it more carefully than anyone had ever looked at a planet of this size, at this distance, in our species' history. To see what was there in the air. To listen, in a sense, for the chemistry of an alien world. To understand why this planet has earned that attention, we have to walk away from Earth for a little while. We have to travel to a star the colour of an ember, and stand at a careful distance, and look at where K2-18b sits in the architecture of its own little solar system. Because the strangeness of this planet starts long before any spectrum was ever measured. The strangeness starts with the kind of sun it has. K2-18 is a red dwarf. That is the simplest way to say it. Red dwarfs are the most common kind of star in the galaxy, by a wide margin. If you could see every star around you, not just the bright ones, you would find that something like 3/4 of the stars in our neighbourhood are these small, cool, red, slow-burning things. Our own sun, by comparison, is unusually bright. Most stars are dimmer than ours. Most stars are smaller than ours. Most stars look more like K2-18. This particular red dwarf has a surface temperature of about 3,450 Kelvin. That is about half the temperature of the sun's surface. Its colour, if you could see it from close up, would be a deep amber, leaning towards orange-red. Not the bright yellow-white of our daytime sky, but something softer, something closer to the colour of a fading coal. The star is also small. Its radius is roughly 45% of the sun's. If you set it down where our sun sits, it would not even fill the same disk in our sky. It is also, in cosmic terms, fairly young, about 2.5 billion years old, give or take. The sun is closer to 4.5, so K2-18 has been burning hydrogen, quietly and slowly, for about half as long as our sun has, and it will continue to burn slowly for an enormously long time. Red dwarfs are the marathon runners of the galaxy. The smallest of them have lifetimes measured in trillions of years. K218 is not that small, but it will outlive our Sun by an order of magnitude all the same. Now, around that small, cool, patient star, K218b orbits at a distance of about 1/7 of an astronomical unit. An astronomical unit is the distance from the Earth to the Sun, so 1/7 of that is very close. Mercury sits at about 1/3. K218b is much closer to its star than Mercury is to ours. Its year lasts only 33 days. By our standards, the planet is sprinting around its Sun. Every 33 of our days, it has completed one full orbit. Every 33 days, it crosses from our line of sight in front of the star's face. And every 33 days, for a few hours, its atmosphere becomes briefly readable by us. Here is the part that should slow you down a little. Even though K218b sits so close to its star, it does not receive an oven's worth of light. Because the star is so much cooler and so much smaller, the actual amount of sunlight K218b gets per square metre of its surface comes out to roughly 1,368 watts. Earth, on the same measure, receives about 1,361. The two numbers are, for all practical purposes, the same. K2-18b is bathed in almost exactly the same amount of light as Earth, just from a different kind of star. That coincidence is part of why this planet matters. If you build a simple physical model of K2-18b, assuming it has a moderately reflective surface, and you ask the model what temperature its top layers would settle at, the answer comes back as roughly 255 Kelvin. Earth, on the same model, is around 257, 2 degrees apart. 2 degrees across 124 light-years and an entire different kind of star. The planet sits, on paper, in what astronomers call the habitable zone of its star, the zone where, if everything else is right, liquid water can exist. But here is the careful thing. Habitable zone does not mean habitable. It means the temperature at the right pressure could allow water to be liquid. Whether there is water on K2-18b or under K2-18b, or whether there is any kind of surface at all, is a separate question, and it is a question that has only deepened with every observation. The planet, when you start asking what it's actually like, refuses to answer cleanly. There are also complications specific to red dwarf systems that any honest discussion has to mention. The first is tidal locking. When a planet orbits a small, cool star at close range, the gravitational forces between them tend to slow the planet's rotation until it shows the same face to the star at all times. One side becomes a permanent day, the other side becomes a permanent night. K2-18b, given its orbit, is almost certainly tidally locked. That changes everything about how its atmosphere would circulate. The day side would be hot, the night side would be cold. Winds and clouds and ocean currents, if any, would have to carry heat from one hemisphere to the other on a permanent scale. Whether a tidally locked Hycean world can sustain liquid water across its whole surface is still an open question in the modelling. The second complication is that red dwarfs are often flare stars. They can release enormous bursts of radiation, sometimes in the form of X-rays or extreme ultraviolet, sometimes in the form of charged particle storms. These flares are short, but they are intense. A young, active red dwarf can strip away the atmospheres of nearby planets over hundreds of millions of years. K2-18 is, fortunately, on the quieter side of the red dwarf population, with only moderate stellar activity. But moderate is not none. Over the planet's lifetime, whatever atmosphere K2-18b started with has been weathered by its star's behaviour. What we are seeing in 2025 may not be what was there 4 billion years ago. For a moment, just hold the picture. A red coal of a star. a planet half a Neptune in size sprinting around it every 33 days, roughly the same warmth as Earth at the cloud tops, a faint orange light bathing whatever surface is down there, if there is a surface at all. One face permanently turned to the star, the other face permanently turned away. That is the place, that is the world Webb has been watching. And yet a habitable zone number on a spreadsheet is not why Webb keeps watching this particular planet. Out of every habitable zone candidate in the catalogue, Webb keeps watching because of what came before Webb. Because the story of K218b did not begin in 2022, when Webb's mirror finally opened. It began 7 years earlier with a different mission in a different decade, with a telescope that was never really supposed to find planets like this at all. In 2013, NASA's Kepler Space Telescope broke. That is the short version. Kepler had been launched in 2009 with a single purpose. It was supposed to stare at one patch of sky in the constellation Cygnus for years and watch for the small repeating dips in starlight that happen when a planet crosses in front of its star. To do that, the telescope had to hold itself extremely still. It had 4 reaction wheels for that job, like tiny gyroscopes, keeping it locked on target. By 2013, 2 of the 4 had failed. A telescope with only 2 working wheels cannot hold itself perfectly still. Without all 4, the original mission was effectively over. Most spacecraft at that point would have been quietly retired. But the team on the ground worked out something clever. They realised that if Kepler used the pressure of sunlight against its own body as a kind of third stabiliser, it could still hold a steady gaze along certain narrow strips of sky. Not anywhere it liked, only along the plane of the ecliptic, where the sunlight came at the right angle. That second life was called K2. In 2015, during the very first campaign of the K2 mission, Kepler stared at a patch of sky in the constellation Leo. Among the thousands of stars in that field, one small red dwarf showed 2 faint dips in its light. The dips were 33 days apart. They were exactly the shape that a transiting planet would produce. The star was given the catalogue name K2-18, and the planet got the lowercase letter b. The detection was clean. It was independent of any telescope that had come before, and it was, in a sense, lucky, because Kepler in its original mission would never have looked at this particular star. For a planet to be more than a flicker in a graph, you need more than a transit. A transit tells you how big the planet is, but not how heavy. To get the mass, you need a second technique. You need to watch the star wobble. As a planet orbits, it tugs at its star, and that tug shows up as a tiny back and forth shift in the star's light, what astronomers call radial velocity. For that, the team turned to a spectrograph in Chile called HARPS, perched on the side of a mountain at the European Southern Observatory's La Silla site. Over the next several years, HARPS watched K218 wobble, and from that wobble the mass came out at roughly 9 times the mass of Earth. HARPS, for the curious, is one of the most precise instruments ever built for measuring the speed of stars. It can detect changes in a star's motion of around 1 meter per second. That is walking pace. Across the gulf of 124 light-years, HARPS can tell when a star is moving towards or away from us at the pace of a slow walk. It does this by splitting the star's light into a high-resolution spectrum and watching how the dark lines in that spectrum, the fingerprints of the elements in the star's outer layers, shift back and forth as the star is pulled by its planets. The shifts are tiny. The instrument is delicate. The measurements take hundreds of nights of patient observation. But over time, the wobble shows up. The planet's mass falls out of the equations, and what was a flicker in a graph becomes a real physical world with a real physical weight. Combined with the transit data, that mass gave a density, and the density was strange. K218b is denser than Neptune but less dense than Earth. It is not a small rocky world like ours. It is not a big puffy world like Neptune. It sits somewhere in between, in a category astronomers were just starting to take seriously around that time, the sub-Neptunes. Planets larger than Earth and smaller than Neptune. There are no examples of this kind of planet in our solar system, none at all, and yet, in the galaxy, they appear to be among the most common worlds out there. Once the planet's basic numbers were locked in, the next question was about its atmosphere. To answer that, the team went to Hubble. The Hubble Space Telescope is older than most people working in astronomy today. It was launched in 1990 and has been steadily looking at the universe ever since. By 2019, Hubble's near-infrared instrument had observed K218b through 9 separate transits, spread across 3 years of careful scheduling. And those 9 transits gave the first glimpse of what was in the planet's air. What Hubble saw was water vapour, faint but consistent. A small but detectable signature in the spectrum at the wavelengths where water absorbs light. That was the headline that broke in 2019, and it was the first time water vapour had ever been confirmed in the atmosphere of a planet in the habitable zone of another star. It was by any honest measure a milestone, but it was also in retrospect a beginning rather than an ending. Hubble could see that water was there. It could not see much else. Its spectrum was a thin slice. Many other molecules hidden in other parts of the infrared were simply outside its reach. That is the gap Webb was built to close. Webb's instruments cover wavelengths that Hubble cannot. Where Hubble can see a window, Webb can see almost the whole wall. So when K2-18b graduated from Hubble's eye to Webb's eye, the question changed. The question was no longer, is there water? The question became, what else is in the air? And to ask that question seriously, with a real answer in mind, somebody first had to propose a guess, a model, a picture of what kind of planet K2-18b might be. That guess had a name and a man behind it. We meet him next, calmly, because he is at the centre of this story whether or not the story he is telling turns out to be the right one. His name is Nikku Madhusudhan, and the world he proposed has a name that did not exist a decade ago. Nikku Madhusudhan works at the University of Cambridge in the Institute of Astronomy. He has spent most of his research career on exoplanet atmospheres, on the chemistry that hides in the spectra of distant worlds. By the time K2-18b became an interesting target, he and his group had already been thinking about a possibility that did not fit neatly into either of the categories most planets are sorted into. A possibility that lived in the gap, not a rocky world like Earth, not a gas world like Neptune, something else, something the textbooks did not have a name for yet. The proposal was this: imagine a planet larger than Earth, but not by much, 2 or 3 times its radius. Around it, a thick atmosphere of mostly hydrogen, the lightest and most abundant gas in the universe. Underneath that atmosphere, instead of rock or magma or a deep gas envelope going down forever, an ocean, a planet-wide ocean of liquid water held in place by the weight of the hydrogen above it. No continents, no coastlines, just one continuous global sea, kilometres deep beneath a dim red sky. Madhusudhan's group called this hypothetical world a Hycean planet. The name is a portmanteau, hydrogen and ocean, Hycean. It is a small linguistic invention, but the science behind it is detailed. The group worked out in a series of papers what the temperature profile of such a planet would look like, what kinds of pressures the ocean would feel at its surface, how the hydrogen atmosphere would behave at different altitudes. They worked out which chemical signatures we would expect to see if we pointed a telescope at one, and importantly, they worked out which of those signatures would be hardest to explain by anything other than life. The argument runs like this. On Earth, certain gases are produced almost exclusively by living organisms. The clearest example is oxygen. Free oxygen on Earth is the product of photosynthesis. If you found oxygen at high concentrations in another planet's atmosphere, you would have a strong reason to suspect biology. But oxygen has problems as a biosignature elsewhere. In a hydrogen-dominated atmosphere, oxygen reacts away quickly. It would not stick around long enough to build up to detectable levels. So if Hycean planets exist, oxygen is not the marker we should look for. There is also another problem with oxygen as a universal marker. Earth had life for more than 2 billion years before its atmosphere accumulated the oxygen we now take for granted. The original microbes did not produce it, or produced it in tiny amounts that were immediately consumed by other chemistry. The Great Oxidation Event, when oxygen finally began to build up in Earth's atmosphere, happened around 2.5 billion years ago, long after life itself had appeared. So even on a world that is teeming with biology, oxygen might be absent for a very long time. A telescope looking at early Earth would have found a planet inhabited by microbes for hundreds of millions of years before it would have found a planet with detectable oxygen. The biosignature we tend to imagine, in other words, is the late-stage one. We need to look for earlier ones. What Madhusudhan's group proposed instead was a small, smelly, sulfur-bearing molecule called dimethyl sulphide. On Earth, this molecule comes almost entirely from marine phytoplankton. It is part of the chemistry of the ocean, part of the salt and iodine smell of a coastline on a warm day. It is produced in vast quantities by single-celled life, and, the group argued, on a Hycean planet with an ocean teeming with similar microbial life, you would expect to see dimethyl sulphide accumulate in the atmosphere at much higher levels than on Earth. Possibly thousands of times higher, possibly high enough to detect with a sufficiently powerful telescope. The reason the concentrations would be so much higher on a Hycean world is partly a matter of geometry and partly a matter of chemistry. On Earth, our oceans cover about 70% of the surface. On a Hycean world, the ocean would be the surface, top to bottom, pole to pole. Every square metre of the planet would be ocean. Any microbial life producing DMS at Earth-like rates would be producing it across a much larger area and into a much thicker atmosphere with different mixing properties. The molecule would have more time to accumulate before being destroyed by ultraviolet light, because hydrogen-dominated atmospheres have different photochemistry than nitrogen-oxygen ones. The combination, in the group's model, was supposed to produce a clean, large, detectable signature, exactly the kind of thing Webb would be designed to look for if we knew where to point it. This was for years a theoretical paper, a prediction, not a claim about K2-18b specifically, a claim about what we should look for if we ever had the means. Then Webb launched, and Webb had the means. Now, before we go any further, the careful thing must be said. Hycean is a model. It is not a measurement. K2-18b might be a Hycean world, or it might not. Other models fit the same numbers. Some research groups have argued, for instance, that K2-18b could be a mini Neptune with no liquid water surface at all, just a deep gas envelope that gets denser and hotter the further down you go. Others have argued it could be a magma ocean planet, with a layer of molten rock beneath the atmosphere instead of liquid water. Each of these alternatives produces a slightly different spectrum. Each of them is consistent with some of the data, and none of them, on its own, is the only possible answer. So the Hycean hypothesis sits in a particular place in the science. It is not a fact. It is a candidate. A candidate that happens to make a clean, testable prediction. If K2-18b is Hycean, and if it has the kind of ocean life that produces dimethyl sulphide on Earth, then a telescope sensitive enough to detect that molecule in its atmosphere should be able to see it. And in 2023, the most sensitive infrared telescope ever built finally turned for the first time towards this exact world, with this exact prediction in mind, to look for this exact gas. What it saw that first time was not a confirmation. It was something more interesting. It was an almost confirmation, a whisper, a signal at the very edge of what Webb's instruments could distinguish from noise. The kind of result that sends a team back to the data again and again, asking the same question. Is that real? Or is that just our hope? The first Webb observations of K218b were taken in early 2023. The team in Cambridge used two of Webb's near-infrared instruments. The first is called NIRIS, which stands for the Near Infrared Imager and Slitless Spectrograph. The second is called NIRSPEC, the Near Infrared Spectrograph. Together they cover the wavelengths from roughly 1 micron to about 5 microns. That covers the part of the infrared where many of the most interesting atmospheric molecules leave their fingerprints. Water, carbon dioxide, methane, ammonia. Each one of those molecules absorbs at characteristic wavelengths, and a careful spectrum can tell them apart. It is worth pausing on what this kind of spectroscopy actually involves, because the picture in most people's heads is wrong. Webb is not photographing the planet. It is not seeing continents or weather or clouds in any visual sense. What Webb is doing is much stranger. It is measuring how much starlight, from K218, makes it through to us at every wavelength when the planet is in front of the star, and comparing that to how much starlight makes it through when the planet is not in front of the star. The difference between the two is the light that passed through the thin sliver of the planet's atmosphere on its way to us. Different molecules absorb different colours of light. Methane absorbs in some places, carbon dioxide absorbs in others. By looking at which colours are missing in the in-transit spectrum, compared to the out-of-transit spectrum, we can work out which molecules the light has passed through. The whole science of exoplanet atmospheres is, in a sense, the science of figuring out what is in a shadow. The data, processed and published later that year, contained two confident detections. The first was methane. The second was carbon dioxide. Both were clearly present in the planet's atmosphere, at levels easy to see in the spectrum. That alone was a significant result. Methane is a gas that, on its own, can have many origins. It can be produced by biology. It can also be produced by deep earth chemistry, by hydrothermal vents, by ancient volcanoes. Carbon dioxide, similarly, is everywhere in the universe. What made the combination interesting was something that was missing. Ammonia. On a planet with a hydrogen-dominated atmosphere, you would expect, by the standard rules of atmospheric chemistry, to see ammonia. And on K218b, the spectrum had almost none. The Hycean model had a clean explanation for that absence. If there is a liquid water ocean beneath the hydrogen atmosphere, ammonia would dissolve into the water and be effectively scrubbed from the air. The mini-Neptune model with no surface did not predict this. The presence of methane and carbon dioxide alongside the apparent absence of ammonia was a pattern that fit the Hycean picture more cleanly than the alternatives. And then, on top of that, there was a third hint. A small, weak signal at a wavelength consistent with dimethyl sulphide, the molecule from the Hycean prediction, the biosignature gas. It was, in the 2023 data, present at very low statistical confidence, below what scientists call 3 sigma, below the level where most researchers would call it a detection. The team in Cambridge, to their credit, did not call it one either. They described it as a tentative hint, something worth following up on, not a discovery. But the world outside the paper read the headlines, not the qualifications. The press cycle that followed in late 2023 was loud. Major news outlets reported, often without the careful framing, that signs of possible life had been spotted in the atmosphere of a distant ocean world. The actual paper had been more cautious than the coverage suggested. The actual scientists had been more cautious than their own press release suggested. But the message in the air, by the time it reached most people's living rooms, was simpler than what the science actually said. A whisper had become a shout somewhere between Cambridge and the front page. Within the exoplanet community, the response was mixed. Some researchers were excited. The methane and carbon dioxide detection alone was solid science, and the Hycean interpretation was at least worth taking seriously. Others were sceptical. They pointed out, fairly, that a tentative signal of a single biosignature gas, at less than 3 sigma, in a single set of observations, was a long way from any kind of confirmed result. The history of exoplanet biosignatures was, they reminded everyone, full of early excitement that had not survived later scrutiny. The K218b signal might be real, or it might be a fluctuation. It would take more data, with a different instrument, before anyone could say with confidence. So the Cambridge team, supported by Webb's scheduling committee, went back. They asked for a third observation. This one would use Webb's mid-infrared instrument, called MIRI, the mid-infrared instrument. MIRI covers a different stretch of wavelengths from about 5 microns to roughly 12. That stretch is the part of the spectrum where dimethyl sulphide actually has its strongest absorption features. NIRIS and NIRSpec had only caught the edge of the molecule's signature, where it was weakest. MIRI, in principle, would catch it where it was strongest. If the gas was really there, MIRI should see it loudly. That MIRI observation was carried out in mid-2024. The data was processed, analysed, and turned into a manuscript over the following months, and in April of 2025 the paper was published. The headline was direct. The strongest evidence yet, the press release said, that life might exist on a planet outside our solar system. We're about to walk into that paper slowly, because it is the central event in this whole story. The pivot point. The moment when a careful, cautious astronomy result became a global headline, and the careful, cautious science around it began to wobble under the weight of the attention. 18 months had passed since the first Webb spectrum. Webb had returned. This time the signal was no longer a whisper. This time it was loud enough to argue about. The 2025 paper was published in the astrophysical journal Letters. Its full title, if you had to write it out, runs to 30 words and includes the phrase "new constraints on DMS and DMDS in the atmosphere of K218b from JWST-MIRI. DMS is dimethyl sulphide. DMDS is dimethyl disulfide. The two molecules are close chemical cousins. Both contain sulfur. Both, on Earth, are produced almost entirely by life. Phytoplankton produce them. Bacteria produce them. They are part of the chemistry of decay and of growth in oceans and damp soils. They are, in a real sense, the smell of a living planet's edges. The MIRI spectrum of K2-18b in the team's analysis showed an absorption signature in exactly the wavelength range where DMS and DMDS leave their fingerprints. The two molecules have overlapping features in this part of the infrared, which means the spectrum alone cannot tell them apart cleanly. It can say only that something in that family of molecules is absorbing light. That by itself was a result. But what made the headline was the abundance the team retrieved from the data. On Earth, dimethyl sulphide sits at concentrations of less than 1 part per billion in the air. That is a tiny fraction, about 1 molecule of DMS for every billion molecules of air. The team's analysis of K218b's atmosphere returned a concentration of more than 10 parts per million. That is 10,000 times higher than Earth's level. Some of their model runs returned even higher numbers. If those numbers are right, the air above K218b's possible ocean is saturated with this molecule. Saturated in a way that, on Earth, would only be explained by an enormous biological flux. the statistical confidence of the detection was reported as 3 sigma. To understand what 3 sigma means, the simplest way is to think of it as a probability. 3 sigma means that if the underlying truth were that there is no DMS in the data at all, there would be roughly a 3 in 1,000 chance of getting a signal this strong by random luck alone. That is unlikely, but not vanishingly unlikely. It is the kind of confidence level that, in physics and astronomy, is treated as suggestive, as worth pursuing, not as a confirmed discovery. The bar for a confirmed scientific discovery, in most of physics and a lot of astronomy, is 5 sigma. 5 sigma means roughly a 1 in 3.5 million chance of being a fluke. That is the threshold at which papers stop using words like indicates and possible, and start using words like detected. The K2-18 BDMS signal in the 2025 paper was about 2 whole sigma below that threshold, closer to the level of a strong hint than the level of a discovery. The Cambridge team's own language reflected this. They did not, in the paper, claim a confirmed biosignature. They claimed strong evidence consistent with a biosignature interpretation under the Hycean model. Outside the paper, the conversation was different. The press release language was bolder. The news coverage was bolder still. By the time the story reached most readers, the phrase "strongest evidence yet of life beyond Earth" had been printed in dozens of major outlets. Headlines have a way of shedding qualifications. 3 sigma became evidence. Evidence became signs. Signs of possible life became, in some places, simply signs of life. The science had a particular shape. The story had grown a different one. Many researchers, in the days that followed, expressed both interest and concern. Sarah Seeger, an astronomer at MIT who has worked on biosignatures for decades, said publicly that she suspected this particular result would remain in the candidate category indefinitely. Kevin Stevenson at the Johns Hopkins Applied Physics Laboratory summarized what he was hearing from his colleagues by saying that the overwhelming consensus inside the exoplanet community was that the enthusiasm of the announcement had exceeded the strength of the evidence. Other voices echoed similar caution. The data was real. The molecule's potential significance, if confirmed, was real. The level of confidence, they argued, did not yet justify the kind of language that was circulating outside the science. This is the part of the story that often gets compressed in retelling. The scientific community did not split into a camp that believed in alien life and a camp that did not. It split into a much smaller, more technical disagreement about what one specific spectrum could and could not tell us. Whether the absorption feature was really DMS, or really a flat line with noise, or really another molecule entirely. Whether the canonical model the Cambridge team used was the right model, or whether other models fit the data just as well. These are not glamorous questions. They are the questions that decide whether a discovery is a discovery, or whether it is a story we will eventually quietly retire. Within weeks of the announcement, a different team at Oxford opened the same data file. They ran their own numbers, and what they found, when they did, sent the conversation in a direction that very few of the original headlines had prepared anyone for. Jake Taylor is a researcher at the University of Oxford. He works on the atmospheres of exoplanets, specifically on the question of how to model spectra carefully enough to know what they are really showing. In May of 2025, a few weeks after the Cambridge paper landed, he published a short note in a journal called Research Notes of the American Astronomical Society. Research Notes is a venue for quick, focused, technical contributions. Not full papers, not headline pieces, just careful, narrow analyses of specific questions in the field. It is worth knowing that Research Notes exists, because most members of the public never encounter this kind of publication. The famous astronomy journals, like Nature or the Astrophysical Journal, publish long refereed papers that can take many months to go through peer review. Research Notes, by contrast, publishes short pieces with lighter review, designed to circulate technical observations and reanalyses quickly. They are not the place where major discoveries are announced. They are the place where the working community speaks to itself, often within weeks of an event, often in response to claims that need a careful technical reply before the broader literature catches up. The existence of this kind of venue is one of the quiet strengths of the modern scientific ecosystem. It means that when a high-profile result appears, other researchers can publish their first technical reactions within a month or two, rather than waiting for the slower journals to catch up. Taylor's note asked a simple question. He took the Miri spectrum of K218b, the same spectrum the Cambridge team had used, and he asked whether the spectrum had any clear features in it at all, or whether instead it could be adequately described by a flat line. A flat line means a spectrum with no detectable absorption features, a spectrum with nothing in it, statistically speaking, a spectrum that, when you fit a model to it, is best explained by saying that whatever is up there, the data alone cannot resolve any particular molecule. His answer, after running the fit carefully, was that the Miri spectrum was well fit by a flat line. That is a strong technical statement. It does not mean there is nothing in K218b's atmosphere. There certainly is. The NIRISS and NIRS-PEC spectra had already shown that, with methane and carbon dioxide. What Taylor's analysis showed was that the Miri spectrum on its own did not contain enough information to robustly say that DMS or DMDS were there. The wiggles in the data were comparable to the noise. If you fit a flat line, you got an acceptable result. If you fit a complex model with DMS and DMDS, you also got a result. The data was not sharp enough to choose between them. That kind of conclusion is, in some ways, more careful than a confident rejection. Taylor did not say there was no DMS on K2-18b. He said the Miri data did not require it. A subtle but important difference. It is the difference between saying we know the answer is no and saying we cannot yet say the answer is yes. And in the world of biosignature science, that difference matters enormously, because the standard is supposed to be high. We are supposed to need clear evidence. The whole project, from oxygen on Earth to DMS on K2-18b, depends on demanding more than a wiggle in a noisy graph. The technical heart of Taylor's note was about how detection significance is calculated. The Cambridge team had used what they called a canonical model, a model that included a particular set of molecules and excluded others. Their argument for excluding the others was that the excluded molecules were unlikely, given the broader picture. But when you exclude molecules from a model, you change the way the Bayesian evidence is calculated. You are in effect telling the analysis not to consider certain alternative explanations, and when the analysis does not consider them, your preferred explanation looks more likely than it might otherwise. Taylor's note pointed out calmly that if you ran the same data through what the Cambridge team called their maximal model, which included a broader range of possible molecules, the signal weakened. The 3 sigma detection of DMS and DMDS on the maximal model did not survive. The data could only reject a featureless spectrum at less than 2 sigma. That is below the threshold most astronomers would treat as suggestive. It is the level at which a serious scientist says the data does not yet support a claim. This is the careful, technical part of how science works. It is not dramatic. It is not personal. Taylor and the Cambridge team are not enemies. They're not on opposite sides of a culture war. They are 2 groups of researchers using slightly different methodological choices on the same data set, arriving at slightly different conclusions and arguing about which set of choices is the more defensible one. That argument is healthy. It is in fact the whole point of having multiple independent groups in a scientific field. If only one group ever looks at any given data, you cannot trust the result. The reanalysis is not a problem, the reanalysis is the work. And Taylor was not alone for very long. Within months of his note, 2 other research groups, working independently, published their own reanalyses. Both of them came to compatible conclusions. The DMS signal in K218b's atmosphere, when the data was looked at carefully, was not as solid as the headlines had said. 3 independent teams, 3 different sets of methodological choices, and a quiet convergence on a conclusion that was, in its essence, the same. We cannot today claim that we have detected those molecules. Then a second team weighed in, and a third, and the picture changed shape entirely. This second team came from Arizona State University. It was led by Luigi Wellbanks, working with Matthew Nixon and several other colleagues. Wellbanks is one of the most active researchers in atmospheric retrieval. The technique of retrieval is what astronomers do when they take a spectrum and ask it questions. You feed the spectrum into a code, you propose various models for what the atmosphere might contain, and you let the code tell you which models fit the data best. Wellbanks has spent years building and testing these codes. His group is widely respected for the careful way they handle the assumptions that go into them. Their 2025 reanalysis of the K2-18b data was substantial. They used multiple independent data reduction pipelines, which means they took the raw data and processed it through different chains of software to make sure the result did not depend on any one set of choices. They ran the resulting spectra through multiple retrieval codes, and what they found across all of these combinations was that DMS and DMDS were not uniquely the best explanation for the spectrum. Other combinations of molecules fit at least as well, and once you included enough alternative possibilities in the analysis, the case for a biosignature interpretation eroded substantially. The third team came from the University of Chicago, led by Raphael Luque. His group's reanalysis, published in the journal Astronomy and Astrophysics in 2025, took the joint analysis a step further. They combined the NIRISS, NIRSPEC, and MIRI data into a single coherent fit. They used 4 different data reduction pipelines, 2 different retrieval codes, and ran the analysis at the highest spectral resolution the data allowed. Their conclusion, when all of this was done, was that the joint dataset showed insufficient evidence for the presence of DMS or DMDs in K218b's atmosphere. The signal, when you looked at all 3 Webb observations together rather than treating MIRI alone, was not there in any robust way. 3 teams, 3 different sets of pipelines, 3 different retrieval codes, and a compatible verdict. The community could not confirm the signal that the Cambridge team had reported. That is the climax of this part of the story, and it is worth slowing down to feel its weight properly. It is not the climax most viewers would expect from a documentary about a possibly inhabited planet. There are no exciting reveals here, no green flashes from telescopes, just the patient, methodical, somewhat anticlimactic work of multiple groups of scientists looking at the same numbers and quietly disagreeing. The technical details of those disagreements are worth understanding because they show how careful this kind of science has to be. Different data reduction pipelines, the software that turns raw telescope output into clean spectra, make different decisions about how to remove instrument effects, how to combine the data from different transits, how to handle the small fluctuations in the star's brightness that are unrelated to the planet. Each pipeline has its own assumptions baked into it. Each one was built by a different team for slightly different purposes. When the Cambridge team published their result, they had used one particular pipeline, processed in one particular way. Wellbanks and his colleagues used multiple pipelines, including pipelines from other groups, and asked whether the DMS signal showed up consistently across all of them. The answer, in their analysis, was that the signal varied significantly depending on which pipeline you used. A robust detection should not depend on the pipeline. A real molecular feature should appear no matter how the data is processed. The K218 BDMS signal, by their measure, did not pass that test. Luque's group took this even further. They asked what happens when you combine all three Webb datasets, NIRIS and NIRSpec and MIRI together, into a single joint fit. The advantage of a joint fit is that it forces a single consistent model to explain the spectrum across all wavelengths at once. If DMS is really present, it should show up in the MIRI data and also be consistent with what the near-infrared instruments saw. If it is only present when you analyze MIRI on its own, it may be an artifact of treating one dataset in isolation. When the Chicago team ran the joint analysis, the DMS signal weakened further. The combined data did not, in their hands, support a robust detection of either DMS or DMDS. The signal that had been 3 sigma in MIRI alone became less than 2 sigma in the joint dataset, below the threshold where most researchers would even call it suggestive. This is what scientific consensus actually looks like most of the time. It is not dramatic. It is a slow convergence of independent analyses, each one slightly different, each one carrying its own assumptions, each one offering its own answer, and then over a year or two the answers start to line up. Or they do not. In the case of K218b's biosignature, the answers, as of where we are now, do not line up in favour of the Cambridge team's strongest claim. They line up against it, carefully, without drama, without a press conference. Just 3 independent papers in 3 different journals, all saying versions of the same thing. Imagine 3 different photographers, each handed the same negative from the same roll of film. Each one takes the negative into their own darkroom. Each one uses slightly different chemistry, slightly different exposure times, slightly different paper. The prints come back. They are not identical. Now imagine arguing about which of the 3 prints shows a face. The negative is the same. The face, if it is there, is the same. But the 3 prints disagree. That is, in a sense, what has been happening with the K2-18b data. The light Webb collected is the same in all 3 reanalyses. What you see in it depends in part on how you develop it. The Cambridge team has not retracted their result. That is important to say. They have not said they were wrong. They have responded to the reanalyses by defending their canonical model, by arguing that their methodological choices are the more physically motivated ones, by pointing out that the alternative analyses also rest on assumptions that can be questioned. They continue to work on K2-18b. They have not gone away. The signal, in their hands, is still there. The question is not closed. It is simply, today, more open than the headlines of April 2025 suggested. This is the part of the story that is most worth holding on to. Webb keeps watching this planet not because the discovery is settled. Webb keeps watching because the discovery is unsettled. Because the data we have is at the very edge of what Webb can resolve. Because every additional transit, every additional spectrum narrows the possibilities by a fraction. Because the question of whether the chemistry of K2-18b's atmosphere can be explained without invoking biology is not a question we have answered yet. It is a question we are still answering, slowly, carefully, one Bayesian retrieval at a time, and then, almost as if the universe wanted to make things harder, another paper arrived, one that did not even address the biology question directly, one that proposed an entirely different kind of answer to what was actually producing the wiggles in the spectrum, an answer that did not need life, an answer that did not even need a Hycean ocean, an answer that came instead from the strange chemistry of dust. In October of 2025, a team led by Yassin Jaziri at the Laboratoire d'Astrophysique de Bordeaux published a paper on K2-18b's atmosphere. Their question was different from the others. They were not asking whether DMS was present. They were asking whether something else could produce features in the spectrum that looked similar, and the something else they had in mind was haze, a planet-wide layer of fine organic particles suspended high in the atmosphere, absorbing light in patterns that, if you were not careful, could mimic the signatures of biological molecules. The particles in question are called tholins. The name comes from a Greek word for muddy, and it was coined by Carl Sagan in the 1970s to describe the dark reddish-brown organic gunk that forms when you take a mixture of simple gases like methane and ammonia and zap it with ultraviolet light. Tholins are everywhere in the outer solar system. They coat the surface of Pluto. They give Saturn's moon Titan its smoggy orange haze. They are produced naturally by atmospheric chemistry, with no biology involved at all. The Bordeaux group's analysis showed that if you include tholin hazes in your model of K218b's atmosphere, you can fit the spectrum reasonably well without needing DMS or DMDS. The haze particles absorb in the same wavelength ranges where the biosignature features appear. They do not require an ocean, they do not require life, they just require the ultraviolet light from the host star to be hitting an upper atmosphere full of methane and other hydrocarbons, which then get broken apart and reassembled into these heavier, darker organic molecules. This is not, in itself, a refutation of the Hycean model, it is an alternative. The Jaziri paper does not claim that K218b definitely has tholin hazes instead of an ocean. It claims that tholin hazes are a viable, non-biological explanation for some of the spectral features that have been interpreted as biosignatures, and it claims this in a way that is hard to dismiss, because the chemistry of tholin formation is well understood. We know how these molecules form. We have made them in laboratories on Earth. They are not an exotic hypothesis. They are a known feature of cold hydrogen atmospheres exposed to starlight. There is in addition another alternative on the table. In 2024, a group led by Oliver Shortall at Cambridge proposed that K218b could be a magma ocean planet. Instead of a global ocean of liquid water beneath a hydrogen atmosphere, the planet might have a deep, hot interior of molten rock. The hydrogen atmosphere above it would interact with that magma in particular ways, producing certain gases and consuming others. The resulting atmosphere, when looked at from far away, would also be consistent with some of the patterns Webb has measured. The Shortall model is a different kind of planet entirely. No ocean, no habitable surface, no place for microbes to swim, just rock, melted, under hot hydrogen. The mechanism behind the magma ocean idea is worth understanding, because it tells you something about how strange these sub-Neptune worlds can be. If K218b formed warm and stayed warm, its rocky interior might never have fully solidified. The bottom of its hydrogen atmosphere might press down on a layer of liquid magma instead of a layer of solid stone. At those pressures and temperatures, the magma would dissolve a great deal of the hydrogen into itself, and certain other gases would be released back upward into the atmosphere as a result. Water vapour, in particular, could be produced from the magma's interaction with hydrogen. Methane could form. The thermodynamics produce a specific chemical signature, different from what you would get above a water ocean, but in places similar enough that the current data cannot fully distinguish between them. A telescope sees the gas in the upper atmosphere. It does not see what is underneath. So now there are three serious candidates for what K218b actually is: Hycean ocean world with possible biosignature gases, mini-Neptune or sub-Neptune with hazy hydrocarbon atmosphere and no surface, magma ocean world with hot rock under a thin gas envelope. Each one fits some of the data. None of them fits all of the data perfectly, and the differences between them in the spectra we currently have are smaller than the uncertainties on our measurements, which means we cannot today choose between them based on the data alone. The other strange thing in the data is the missing ammonia. As we mentioned earlier, ammonia should be present in a hydrogen-dominated atmosphere by the standard rules of thermochemistry. K218b's atmosphere has almost none. The Hycean model explains this by saying the ammonia is dissolving into an ocean. The mini-Neptune model has a harder time explaining it cleanly. The magma ocean model offers some possibilities, but they require fine-tuned chemistry. And the haze model has yet another set of possibilities, involving photochemistry destroying ammonia before it can build up. None of these explanations is decisively better than the others. The missing methane and ammonia question is, as of the time of this script, still considered an unresolved puzzle in sub-Neptune atmospheric chemistry. The picture you should hold in your head by now is one of careful uncertainty. K218b is not a planet about which we know nothing. We know its size, we know its mass, we know it sits in the habitable zone of its star. We know its atmosphere contains methane and carbon dioxide at high confidence. We know it does not contain much ammonia. We know its sky is, on some level, doing something chemical that we have not yet seen elsewhere. And we know that what that something is exactly has now been argued about by enough independent groups that the simplest summary is the honest one. We do not yet know what K218b is, and that is why Webb keeps coming back. The planet sits unresolved in Leo. Its star continues to burn its slow red light. The chemistry above its possible ocean, or its possible hazes, or its possible magma, continues to unfold in patterns that filter the starlight passing through it. Webb has scheduled time to look again. What it sees next will not settle the question on its own, but it will slowly narrow the possibilities. Webb's schedule is one of the most contested resources in modern astronomy. There are far more good ideas for what to point it at than there is telescope time available to look. Every 6 months or so, a committee at the Space Telescope Science Institute receives thousands of proposals. They review them, they argue, they rank them, they allocate hours, and almost always more hours are requested than can be given. Getting Webb time once is hard. Getting it 3 times for one planet is unusual. Getting it 4 times for the same planet is the kind of decision that has to be defended carefully. But for K218b, the case is straightforward. The current data is good but not conclusive. The molecules in question, if they are there, are right at the edge of Webb's ability to detect them. More transits, observed in the same wavelength ranges, would tighten the error bars on every measurement. With enough transits, the noise in the data would shrink, and the wiggles in the spectrum would either grow into clear features or fade away to nothing. Either outcome would be informative. A clearer detection would strengthen the biosignature hypothesis. A clearer non-detection would weaken it. Both are valuable. Both are worth telescope time. There is also the question of which wavelengths to focus on. The April 2025 controversy was specifically about the Miri spectrum. A future observation could collect more Miri data, or it could add new wavelength coverage that none of the previous observations had. Each instrument on Webb sees a different part of the infrared, and each part of the infrared carries a different set of molecular fingerprints. Filling in the gaps between the previous observations in principle would help distinguish DMS from hazes, methane from carbon dioxide, ocean from magma. The chemistry of K2-18b, in other words, is hiding in plain sight in the parts of the spectrum we have not yet looked at carefully enough. Beyond Webb, there are future missions on the drawing board that could help, but they are not yet built. The most relevant one for habitable zone exoplanets is a concept called the Habitable Worlds Observatory. It is being designed by NASA as a successor to Hubble and Webb, with capabilities specifically aimed at the problem of finding and characterizing biosignatures on Earth-like worlds. The observatory is still in the conceptual phase. Its detailed design is being worked out. Realistically, it will not launch before the late 2030s, and possibly later. Anything it tells us about K218b will be a decade or more away. In the meantime, the planet sits and Webb watches, and other ground-based observatories on Earth also continue to contribute. Radial velocity measurements with newer spectrographs can refine the mass of the planet to better than they did with HARPS in the 2000s. High-resolution spectroscopy from the largest ground-based telescopes, like the Very Large Telescope in Chile, can sometimes detect individual molecules in exoplanet atmospheres by their specific fingerprints. None of these techniques by themselves will resolve the K2-18b question, but together, over years, they will keep adding pieces to the puzzle. A new generation of ground-based telescopes is also under construction. The largest of them is being built on a mountain in the Atacama Desert in Chile. It is called the Extremely Large Telescope, and when it sees first light in the next few years, it will have a primary mirror almost 40 meters across, roughly 6 times the diameter of Webb's mirror and almost 40 times the collecting area. From the ground, it cannot match Webb's perfect infrared darkness, because the Earth's atmosphere glows in the infrared, and the atmosphere itself absorbs many of the wavelengths we want to see. But for certain specific molecules, at certain wavelengths where the atmosphere is more transparent, a ground-based telescope of that size will be able to gather signals that no current instrument can match. K218b will be one of its targets. The ELT is unlikely to settle the biosignature question alone, but it will add another independent measurement with a different instrument on the same world. That is how the puzzle gets solved eventually, not by any single telescope. By a chorus of them, each adding its own voice. This is how exoplanet science works in practice. It is not a single dramatic moment. It is a long, slow process of accumulating evidence, of building up a picture, one observation at a time, one paper at a time, until the picture is clear enough that even the most cautious researchers agree on what it shows. Some planets have already gone through that process. Their characters are now reasonably well established. K218b is not one of those planets yet. K218b is in the middle of the process, right in the middle, and we are watching that process unfold in real time in our own decade. There is something quietly thrilling about that, even if the public conversation has mostly focused on whether life has been found. The thrill is not the finding. The thrill is the carefulness. The thrill is that, for the first time in our species' history, we have a telescope sensitive enough to ask a serious question about the atmosphere of a planet beyond our solar system, and we have multiple research groups serious enough to argue carefully about the answers. The argument is not a failure. The argument is the science working as it should. The argument is what truth looks like before it is settled, and the settling, when it eventually comes, may not come all at once. It may come the way most scientific settling does, slowly, paper by paper, observation by observation, until one day someone gives a talk and refers to K218b's atmosphere in the past tense. We know what it is, they will say. We figured it out. It took 20 years. Here is the answer. And the answer might be life, or it might be hazes, or it might be magma, or it might be something none of us today have thought to predict. Whatever it turns out to be, the path to it will run through the kind of work we have just walked through tonight, which leaves one last question. Not about the planet, about the story itself, what this whole long, careful, contested investigation is actually about when you stand back from it. A planet, 124 light-years away, in the constellation Leo. A red dwarf star, smaller and cooler than the Sun, burning slowly through its hydrogen. A world that may have an ocean, or may have hazes, or may have magma. A telescope, 1.5 million kilometers beyond Earth, returning to look at this one planet, again and again, because the chemistry of its atmosphere refuses to settle into a clean answer. A team in Cambridge that proposed an interpretation, 3 other teams that, looking at the same data, found that interpretation harder to support than the original paper suggested. A community of scientists still working, still arguing, still careful. That is the literal shape of the story. But the story has a quieter shape underneath it, and the quieter shape, if you will allow it, is what this script has really been about. The quieter shape is this. We have built a telescope. We have pointed it at a smudge of light around a star almost nobody can see with the naked eye. We've collected the few photons that pass through that smudge's atmosphere and reach us across 124 years of empty space. And then we have argued, carefully, politely, repeatedly, about what those photons are telling us, about whether the patterns in them mean what we hoped they meant, about what kind of place that distant world might be. That is an extraordinary thing for a species to be doing. Not the answer, the asking. The fact that, in our current decade, we are equipped to argue about the chemistry of an alien sky. The fact that we have, between Cambridge and Oxford, and Arizona and Chicago and Bordeaux and several other institutions, enough careful people working on this one specific question that the answer will eventually be as solid as we can possibly make it. The fact that the argument is happening at all. The fact that we care. It would have been easy in the days after the April 2025 paper to call the question settled, to say, yes, this is life, this is the discovery, this is the moment we have been waiting for, and move on. Some of the press coverage came close to doing exactly that. But the science did not. The science slowed down. It opened the data file again. It ran the numbers again. It published the slower, less exciting follow-ups in technical journals that most readers will never see. It did the work, in other words. It did the work the headlines did not have time for. There is a kind of comfort in that, on a night when you might be drifting off. The comfort is not that we have found life elsewhere. We have not. The comfort is that, even when a discovery is announced with great fanfare, there are people who quietly check the math. There are people who run the analysis a second time, a third time, with different assumptions, just to be sure. There are people who publish notes pointing out small but important inconsistencies. There are people who are willing to say, in a public, technical, professional voice, the data does not yet support that claim. That is how we end up knowing anything. Not through the bold first announcements, although those have their place. Through the slow, patient, sometimes deflating second look. Through the willingness of one careful scientist to read another careful scientist's paper and say, respectfully, I do not think you have shown what you think you have shown. Through the quiet conversation in the margins, far from the press releases where the actual settling happens. K218b is one planet. We may in time learn that its atmosphere is rich with biology, or we may learn that its atmosphere is rich with hazes and rocks and chemistry we did not anticipate. We may learn one thing or the other within the next decade, or it may take much longer. The planet will continue to orbit its small red sun every 33 days, whether we settle the question or not. Webb will continue to look at it. New instruments in time will join Webb, and the story will at some point end, or rather, it will resolve. It will become the kind of question we discuss in past tense. For tonight, though, the question is still open. The data is still being argued over. The planet is still, in the careful language of the field, a candidate for many things. A Hycean world, a mini Neptune, a magma planet, a place where life might exist, a place where life almost certainly does not. We do not yet know. And not yet knowing is not a failure. Not yet knowing is the honest position, given the data we have today. If you're lying somewhere as you listen to this, in a room that is probably dark by now, on a planet that is, by any reasonable measure, full of life, you can take a small comfort in the fact that we live in a time when a question like this can even be asked. A century ago, we did not have the tools. A few decades ago, we didn't have the telescopes. Last decade, we did not have the spectroscopy. This decade, we do, and we are using it. Slowly, with mistakes, with arguments, with revisions, but using it. Somewhere above the Earth, a 6.5-metre golden mirror is still pointed at the sky. It has had a quiet night. Its instruments are cool, its electronics are humming, its alignment is holding. In some future scheduling block, perhaps in the coming year, perhaps the one after, it will turn again towards Leo. It will wait for the small red star K218 to dim slightly, as a planet 2.5 times the size of Earth crosses in front of it. For a few hours, the starlight will filter through that planet's atmosphere on its way to us. Webb will collect it. The data will be downloaded, processed, and added to the file. And somewhere on Earth, in a series of offices and laboratories spread across at least 4 continents, a number of careful people will open that file. They will run their analyses. They will argue in print about what the new data does and does not show. And the picture of K218b will become, by a small fraction, clearer than it is tonight. That is the planet James Webb cannot stop watching. That is why it keeps coming back. Not because we already know what is there, because we do not. And because, for the first time in our species' history, we have a telescope and the patience and the carefulness to find out. The light from K218 left its star 124 years ago. It has been travelling in the dark since before most of us were born. It will keep arriving for as long as the star keeps burning. There is no rush. Good night.